Hello, my name is Richard Harpster, and I'd like to welcome you to the RAMS 2022 conference, where I will be presenting the AIAG-VDA and SAE J1739 DFMEA methods, similarities, differences, and impact on the auto industry. During the presentation, we will be covering 6 basic topics. The first topic will be the historical role of the AIAG-VDA and SAE in design FMEA use. The second topic will be the fundamentals of the AIAG-VDA DFMEA method. Thirdly, we will look at the fundamentals of the SAE J1739 DFMEA method. For purposes of comparison, we will then go over a few basic design FMEA fundamentals. We'll use these fundamentals to assess the effectiveness of these two new methodologies. In a summary and conclusion, we will talk about both the benefits and the weaknesses of these new methodologies. Historically, the AIAG has been responsible for FMEAs within the North American automotive industry. The VDA, on the other hand, has been responsible for the implementation of FMEAs in the German automotive sector. The role of the SAE basically has been to support the implementation of FMEAs within the North American automotive industry as well. Now, historically, both the AIAG and SAE FMEA manuals have been technical equivalents of each other. The easiest way to understand the AIAG-VDA DFMEA process is to understand the VDA software on which it is based. The VDA software that drives the VDA FMEA methodology was jointly developed by Mercedes-Benz AG, BMW AG, Siemens AG, and a small company owned by Peter Rosenbeck, who created the original software on which the VDA methodology is based. Mr. Rosenbeck had been hired by Siemens AG in 1988 to develop a failure diagnostic system with fault-free elements for a semiconductor production process. The original software was called Object FMEA. At the time, many people treated the FMEA like a fault tree, so the conversion of Rosenbeck's fault tree software to FMEA software was a natural step. The original VDA FMEA software was called APIS IQ FMEA 2.0 and was first distributed by Daimler-Benz Inner Services in 1992. Daimler-Benz Inner Services would distribute the software until 1996, when the first VDA FMEA manual was published. Many complained the new FMEA manual was a user's manual for the software. The foundation of the VDA DFMEA methodology, which again is software-based, is the product fault tree. The product fault tree is created by creating and performing 3 different analyses. The first analysis is the structure analysis. The second analysis is the function analysis. And the third analysis is the failure analysis. The structure analysis consists of identifying the assemblies, subassemblies, components, and characteristics that make up the components. So what you see here is the structure of the seat motor, which sits on top of the commutation system, which then sits on top of the brush card body, and then you see the characteristic of the brush card body called the base body wall thickness. Once the structure analysis is created, the next thing to do is the function analysis. So for each of the individual assemblies, subassembly components, and characteristics, we have specifications. So that's what you see here. So it's in the case of the seat motor has to convert the electrical energy to mechanical energy according to a certain parameterization. The final step of creation of the product fault tree is the failure analysis. One then writes the failure modes of each of the functions that have been listed in the flow diagram. So what you see here is the completed product fault tree for the AIAG-VDA methodology. Once the product fault tree is created, the next step is to take the information and place it in the FMEA form. Now, the AIAG-VDA methodology has multiple DFMEA forms. We're going to use Form A. In Form A, Step 2 is called Structure Analysis. And what you can see here is we see the next higher level focus element and next lower level are characteristics. Now, the focus element is the type of element, the assembly, subassembly, or components that the design FMEA is being performed on. So in this particular case, our focus element is going to be the commutation system. Now the level that sits above it, since this is a subassembly, would be the assembly, so the next higher level would be the seat motor. And then the level that sits below the subassembly would be the component. So in this particular case, in the case of the commutation system, DFMEA, that next lower level would be a component, which would be the brush card body. Then what we see in step number 3 is we list the individual functions for these 3 elements. So the next higher level function, we got the second level, which is the actual focus element function, and then finally the component level function here. And then the final step is to take your failure analysis and then populate step 4 of the form. And so you can basically see that we've populated the failure modes of these 3 elements in this failure analysis section of the design FMEA. The next step of the process is to add the FMEA related columns that aren't part of the product fault tree. So the first thing we need is ratings. So we have a severity rating column, an occurrence rating column, and detection rating column. We also see that we have 2 types of detection or design controls, current prevention controls and current detection controls. We have a new column here that isn't present in the AIG 4th edition DFMEA, which is called the DFMEA AP or action priority. This replaces the risk priority number for determining what to work on. And over here in section 6, this is where we're going to put our recommended actions, which in the new methodology is called the optimization section. When it comes to the design FMEA, one of the most important things to determine is what is it you should be working on. And in the AIAG-VDA methodology, the method used to determine what to work on is what we call the action priority, or AP. It consists of the table that you see in front of you. In the first column, we have the effect. In the second column, we have a severity range. In the third column, we have an occurrence range. And then here we have the ability to detect and the detection range. And to these various combinations of rating, we assign a H, a high priority, you have to work on it, M, medium priority, and L, low priority. Now, if we look at the various ratings, what we find out is that typically in a design FMEA, occurrence should be the probability of the failure mode due to the cause. However, in the AIAG-VDA DFMEA method, the occurrence is basically based on the maturity of the design. How old is the design? If it's a new design, the occurrences tend to be higher. And if it's an existing mature design, the occurrences tend to be lower. It has nothing to do with the probability of failure, but rather than the maturity of the design. The second thing that we see is that the detection control rating system is based on the effectiveness of the design controls, and this becomes part of the AP process. Now, the issue that we will see is that when you include the detection rating in the AP calculation, this AP no longer means risk alone, but can take on a totally different meaning, and we're going to explain that later on. Although I don't know the exact number of people who were on the AIAG-VDA committee and the SAE J1739 committee, there was considerable overlap. And because of this, you can see a lot of similarities between the new AIAG-VDA Handbook and the SAE J1739 DFMEA method. As is the case with the AIAG-VDA and the SAE, you will create design FMEAs for individual system, subsystem, and component DFMEAs. You will also create a structure tree where you will show these various system, subsystem, or component DFMEAs. Like the AIAG-VDA, you will have severity, occurrence, and detection ratings, and you're going to find that these ratings are basically the same between the 2 methodologies. And also, like the AIAG, the SAE J1739 has adopted the action priority, or AP method, used to determine what to work on. In the SAE J1739 methodology, the AIAG-VDA function analysis is replaced by an item function matrix. So what you do in this particular matrix is in the first column, you would list the element that would show up in the function in the structure. So in this particular case, this particular design FMEA will be done on the wiper system level. The next thing is to list the function of that particular element, which in this case is to clear the windshield of precipitation on all wiper speed settings. Now there's an additional column they allow you to add that does not show up in the function analysis tree called requirements. And in here you can list the various details of these requirements. The only problem is this information is not used in the construction of the failure modes. So the problem arises is that you are writing failure modes, it's against a very general description rather than writing failure modes against a very specific set of design requirements. This will also impact our ability to create and define the proper design verification. In this item function matrix, we give these functions priorities, and what happens is during the SAE J1739, you may decide to scope your design FMEA down by maybe only working on high priority items. Then if there's an external interface between this particular item and the outside, that interface is listed here. And if there's any internal interface types, those are listed here. As it states here, the failure analysis is not performed. So you will have a structure tree. You will have the equivalent of a function analysis tree, but you will not have a design failure analysis tree as you did in the AIAG-VDA methodology. Let's now look at the fundamentals of performing a design FMEA to reduce design-related risk. One of the common misunderstandings of design FMEAs, because of the name Design Failure Mode Effect Analysis, is that the purpose of the design FMEA is to determine all of the possible failure modes and then to try to mitigate the effects of those failures. That is not the purpose of a design FMEA. The design FMEA is a risk assessment of the adequacy of the hardware specs and or software code before it's released to manufacture. So what you see here is 7 key steps that must be taken before we can determine whether or not we can release that particular set of design hardware specs and software code. The first thing is we have to define the design requirements. Now there are 17 different types of design requirements that one should consider. In the original FMEAs and in the case of the SAE and the AIAG-VDA, the only requirements considered were function. However, there's many other different types of requirements one can have. One is sensory. For example, I'm sure in many of your companies have had perfectly functioning product returned because of the way it looked. People did not like the way it looked, or maybe people did not like the way it sounded. So the bottom line is when doing the design FMEA, you must think of all design requirements and not just function. Once you list the various requirements, then you list how you can fail to meet them. And anytime you fail to meet them, that is what we call an objectionable incident. The next thing we have to do is for each of those objectionable incidents, we have to define the possible harms and severity of the harms. Now, an individual incident can have many different types of harms with different severities. Now, the original FMEA practitioners try to define for each of the individual objectionable incidents or failures of the product all the different harms and all the different severities, and what they realized, there were so many of them they couldn't do it. So in the modern FMEA, what we do is we find the worst case harm with the worst case severity, and we assign that to all failure modes, even though we know we'll actually be overstating the potential harm from the design for that particular failure. Once we identify the failure mode and the harm, the next step is to identify the root cause. And it's very important when defining the root cause of a particular failure that you either define a hardware spec that has been incorrectly set, or you define software code that has been improperly written. Those are the only allowable entries in the cause column of the design FMEA. We're going to see that both the AIAG-VDA and SAE J1739 violate this basic principle. Once we identify the causes and we have the modes, the next step is to find the probability of each of the failures due to each individual cause. What we're trying to do, risk has a severity component and a probability of occurrence component, and we're trying to find those failure mode cause combinations that provide the greatest risk. Which brings us to the next column, which is the class column. This is where you put the class symbol. This column is typically misused. People basically just look at characteristics and say, oh, that's a safety characteristic, I'm going to put a symbol on it. Or that's a function characteristic, I'm going to put a symbol on it. It's not the purpose of this column. The purpose of this column is to identify the residual risk due to the failure mode in combination with the cause. So basically you need a severity rating and you need an occurrence rating to determine whether or not you have a class symbol on that row. And when you do have that symbol, that means that row of the FMEA represents objectionable risk. What we then do is any row of the FMEA that has a symbol, we now know we have to work on. So based on the presence of a symbol in the class column, we then do recommended actions. We monitor those recommended actions and we monitor the changes in severity and occurrence. And if they go down and make the symbol go away, then we know we remove that residual risk. So the bottom line is, so we're going to use a combination of residual risk and design benefits because we're not going to be able to remove all the risk from the design. When we compare the AIAG-VDA and SAE DFMEA methods to the basic FMEA fundamentals, we see there's some real problems. The first thing we see is since these two methods require you to define functional requirements for every assembly, subassembly, and component, what we find is that people write very generic statements in the requirements column of the design FMEA. The second thing we see is that because these are very generic statements, the failure modes tend to become very, very generic. And when you take the combination of these two, it makes it very difficult to create a very good design verification plan to assess the adequacy of your design. When it comes to the cause column of the design FMEA, what we find when we look at AIAG-VDA and SAE DFMEA methods is that whenever the design FMEA is a subassembly or an assembly, the failure cause is always in the form of another failure mode. As an example, when you have an assembly design FMEA, the failure mode is some form of subassembly failure. And when you have a subassembly design FMEA, the failure mode cause is some form of component failure. It's only when you have a component failure that the failure cause is in the form of a characteristic spec and a condition. So what we see is that the system FMEAs and the subassembly design FMEAs created using both the AIAG-VDA and SAE FMEA methods result in failure modes being put in the failure cause column. When it comes to probability, because both the SAE and AIAG-VDA method allow the placement of a failure mode in the cause column, they define the probability rating as the probability of the cause and not as a probability of the failure mode due to the cause. This basically destroys the fundamental purpose of defining risk to manage your design and determine whether or not it should be released. The AP risk evaluation uses both the incorrect definition of cause and also introduces the concept of adding detection into the residual risk assessment. The bottom line is in a design, once the design is released, it's gone. So the effectiveness of your detection has no impact whatsoever on the residual risk in the design. And then finally, because you're not using residual risk to determine what to work on, you cannot do as the fundamental design FMEA does, which is uses residual risk to determine what you should be working on. Both the AIAG-VDA and SAE DFMEA methods do not meet the requirements of the design FMEA fundamental slides that I've shown you. When you use these particular methods, the first thing you're going to see is that you're less effective at managing risk. The biggest two reasons for this is the lack of details in the functional requirement, the failure to include non-functional related design requirements, and thirdly, when it comes to assembly and sub-assemblies, the presence of failure mode in the failure cause column. Also, you're going to be considerably less efficient in implementing your FMEAs because now you must create a design FMEA for every assembly, sub-assembly, and component in your design. And this is going to take considerable time. Both General Motors and Ford allow the use of the AIAG-VDA FMEA Handbook, but do not require its use as a customer-specific requirement. Only Stellantis recommends the use of the AIAG-VDA FMEA Handbook as an IATF 16949 customer-specific requirement. A company can use another method with permission. Obviously, the European companies who have already been using the VDA method will require the use of the AIAG-VDA method since it is based on the original VDA methodology. To date, no companies have mentioned the SAE J1739 FMEA Standard in their IATF 16949 customer-specific requirements. If you have any questions, please feel free to call me either at my cell phone or at my office or email me as well. Thank you very much for your time.